In this module, we shall discuss hypothesis testing from the viewpoint of nonparametric inference. In nonparametric inference, the tests are far from optimal because we don't have Neyman-Pearson lemma and likelihood ratio methods of test construction. So, the only concern is consistency of tests. So, in this module, we shall discuss consistency in details. Finally, we shall provide a method to obtain distribution-free confidence intervals for the unknown parameters or say unknown location parameters. We start with the need of non-parametric hypothesis testing. The entire classical inference is based on the assumption regarding the underlying population. Hence, these procedures are valid as long as these assumptions are satisfied. For example, students' t-test is appropriate only when the underlying distribution is normal. But there are non-normal distributions having applications in real life. Therefore, inference based on t-test when the actual distribution is non-normal may be misleading. Thus, it will be better if hypothesis testing procedures can be developed with minimal set of assumptions like continuity or symmetry about the underlying distribution. Suppose there exists a statistic t relevant to the testing problem such that the exact or conditional or asymptotic distribution of t under the null hypothesis is independent of the underlying distribution. Naturally, the significance level for the test based on t does not depend on the underlying distribution. That is, these tests are level robust. Tests based on such a t are termed as non-parametric or distribution free. T is often formed by taking only the signs or ranks of the actual observations. Naturally, the full information contained in the individual observation is ignored. Hence, tests based on T are often less efficient than their parametric counterparts. However, non-parametric tests are the good alternatives as long as the validity of the underlying distribution is questionable. Next, we discuss different components of a non-parametric test. Non-parametric inference is developed without considering any specific underlying distribution. Thus, the available methods like Neyman-Pearson lemma or likelihood ratio method of test construction are of no use. Hence, we need to develop tests from very basic quantities like signs, ranks, the number of runs, etc. In particular, our main emphasis will be on identifying a non-parametric distribution-free statistic t and its nature when there is a deviation from the null hypothesis. So, we shall assume that a non-parametric hypothesis testing problem comprises of the following components. Number 1, model assumption, that is, the minimal set of assumptions about the underlying distribution. Next, hypothesis of interest, that is, whether our interest is in location or scale parameter or else. Next, suggesting a distribution-free statistic, that is, specifying some statistic t. And then, justifying the form of critical region. And of course, this justification is based on some intuitive appeal. Next, we investigate unbiasedness, consistency of the suggested test, and then provide a large sample test suggested by the asymptotic distribution of t. And lastly, in some situations, deriving a distribution-free confidence interval. Non-parametric tests are often developed from intuitive justification, and hence they are far from being optimal. Consistency in this context is therefore an important concern to measure sensitivity of the test to a little departure from the null value in large samples. Roughly speaking, if the power function approaches unity as n tends to infinity, the concerned test is called consistent. In fact, as we increase n, we get more and more information and hence our decision is likely to become more accurate. However, in non-parametric inference, consistency is defined in a specific way. Specific definition assume x1, x2, xn as IID observations from an unknown distribution G. To test the null hypothesis that G belongs to some omega naught against the alternative that G belongs to some omega A, where omega naught is a class of distributions specified by the null hypothesis and omega A is a class of distributions specified by the alternative hypothesis. Then a sequence of tests phi n is said to be consistent if for every g specified by the alternative hypothesis, expected value of phi n tends to 1 as n tends to infinity. Here, expected value of phi n under the alternative is nothing but the power function of phi. However, such a definition is not easy to check and we need some simpler conditions. Now, we shall provide a sufficient condition for consistency, which will be easier to verify in practice. Assume that phi n is a right-tail test based on a statistic Tn. Then, phi n is consistent if, number 1, phi n is asymptotically size alpha, that is, expected value of phi n tends to alpha where g is specified by the null hypothesis for every g. And number 2, Tn, the statistic under consideration, convergence in probability to some function mu g, where mu g equal to mu naught for every g belonging to omega naught and mu g greater than mu naught for every g belonging to omega a. However, the requirement on asymptotic size is not immediate in practice. But if we can establish asymptotic normality of Tn for all g belonging to omega naught, then the requirements in 1 and 2 above are automatically satisfied. Therefore, if there exists a positive constant sigma naught such that as n tends to infinity, square root of n Tn minus mu naught divided by sigma naught convergence in distribution to normal 0 1 for every g specified by the null hypothesis, then phi n is consistent. Thus, asymptotic normality is a stronger condition than those required in consistency. We have discussed consistency and sufficient conditions for consistency. Thus, it will be interesting to know the consequence of lack of consistency. We explain this phenomena through an example. Suppose x1, x2, xn are IID observations from a Cauchy distribution with location parameter theta. Consider testing theta equal to theta naught against the alternative theta greater than theta naught. We suggest two possible tests. Test 1. Test 1 rejects the null hypothesis if the observed value of x bar minus theta naught exceeds c, where c is determined such that the test has size 0.05. Since under the null hypothesis x bar minus theta naught has a standard Cauchy distribution, we get c as 6.314. The power function is naturally beta 1 theta equal to probability that w exceeds theta naught minus theta plus 6.314, where w is again has a Cauchy distribution. However, the second test is based on the sample median x curl, and this test rejects the null hypothesis if the observed value of x curl minus theta naught exceeds some c dash, where c dash is as usual calculated from the size condition. That is, c dash is such that probability that x curl minus theta naught exceeds c dash under the null hypothesis is 0.05. Now, it is known that square root of n x curl minus theta is asymptotically normal 0 pi square by 4 under any theta. Thus, we set c dash as 2.584 divided by square root of n. Then the power function becomes beta 2 theta equal to probability x bar x curl minus theta greater than theta naught plus 2.584 by square root of n, and this probability is evaluated under theta. Now, both the tests are asymptotically size 0.05. The latter is based on an asymptotically normal statistic, whereas the former involves an inconsistent statistic. For better understanding the effect of consistency on power, we provide a plot of both the power functions taking theta naught equal to 0. We compute powers for 3 choices of theta and plot the power for various values of the sample size n. This can be seen in the next figure. So, for an explanation of the relative merits or demerits, we consider theta naught equal to 0 and theta as 0.2. Then, it is easy to observe that the power for test 1 remains very close to 0.05 for varying n, but the power for test 2 increases sharply as n increases. The same is observed for the other choices of theta. However, power of test 2 increases at a higher rate than test 1 for increasing values of theta. This is expected as the first test is based on an inconsistent estimator. Thus, it does not concentrate around the true value for large n and hence the power increases at a very slow rate. On the other hand, x curl, the sample median, is consistent and hence for large n approaches the true parameter and consequently power increases for increasing values of n. Next, we shall discuss different types of hypothesis testing problems in non-parametric inference. We start with single sample problems. In a single sample problem of location, we consider a hypothesis regarding the population quantiles assuming continuity or symmetry, and sometimes we assume continuity and symmetry both. There is another type of single sample problem, namely goodness of fit problem. In a goodness of fit problem, the interest lies in investigating whether the sample comes from a specified distribution. However, the alternative in such a problem is not conclusive. That is, once the null hypothesis is rejected, we cannot give any idea about the underlying distribution. Now, we discuss different two-sample problems. Specifically, in a two-sample problem, we have data from two independent populations indexed by the distribution functions fx and gx. The basic hypothesis in any two-sample problem is fx equal to gx for every x against the usual one-sided or two-sided alternatives. Now, we have either a homogeneity alternative or a stochastic alternative or a location alternative or a scale alternative. So, we start with homogeneity and stochastic alternatives. Suppose that two underlying populations differ in any manner, that is in location or in scale or in skewness. Then the homogeneity alternative can be expressed as fx not equal to gx for some x. Next, suppose that x observations tend to be larger than y. That is, probability x greater than equal to small x is greater than probability that capital Y greater than equal to small x for every x. That is, in other words, x is stochastically larger than y. Then a stochastic alternative is taken as gx greater than equal to fx for all x with strict inequality for some x. Next, we have location alternatives. Suppose it is anticipated that the underlying distributions differ only in location. That is, gx equal to fx minus theta for some real valued parameter theta. Now, fx greater than gx or fx equal to gx or fx less than gx according as theta less than 0 or theta equal to 0 or theta greater than 0. Then, in a location problem, the null hypothesis can be restated as theta equal to 0 and the alternative is either theta greater than 0 or theta less than 0 or theta not equal to 0. Then it is worthwhile to mention that location alternative is a special case of a stochastic alternative when gx is taken as fx minus theta. However, in general, gx greater than fx indicates larger y observations and hence corresponds to larger location of y observations. Hence, stochastic alternative relates to the location alternative in some sense. We, in addition, provide some plot fx minus theta and the corresponding density f small f x minus theta. If we look at the leftmost figure corresponding to f capital F x minus theta, we find that the function fx minus theta corresponding to theta less than 0 is shifted towards the left, whereas fx minus theta for theta greater than 0 is the rightmost. Thus, probability of getting a higher observation for theta greater than 0 is higher than those for theta equal to 0 and theta less than 0. Next, we shall consider scale alternatives. Suppose it is anticipated that the underlying distributions vary only in terms of scale. That is, gx equal to f of x by sigma for some positive sigma. Then fx is greater than gx only when sigma greater than 1, fx equal to gx when and only when sigma equal to 1, and fx is less than gx when sigma is less than 1. Thus, the null hypothesis reduces to sigma equal to 1. The alternative is either sigma greater than 1 or sigma less than 1 or sigma not equal to 1. Thus, scale alternative can also be viewed as a stochastic alternative where gx equal to f of x by sigma. Often, we have data for two time points from a single unit or individual. Naturally, observations are paired and hence are correlated. For example, the responses of a patient before and after a drug is administered are associated. Suppose xi, yi are the n pairs of observations from some bivariate distribution fxy, where this bivariate distribution is unknown and has the marginals fx and fy. Then we have the following two hypotheses which are of main interest. Number one, the problem of association. Here, the interest lies in testing that the two random variables x and y are independent. That is, the joint distribution function is the product of the two marginals for every pair of xy. Next comes the problem of location. Suppose x is the response before an event and y denote that after the occurrence of that event. That is, if we consider the drug example as discussed earlier, we might be interested in determining whether the drug has any effect on the responses. Now, if we define the difference d as y minus x, then the null hypothesis states that the distribution of d has median at the origin. Now, we shall give a general procedure to obtain a distribution-free confidence interval for the population quantile when observations are taken from a continuous population. Suppose xi, I from 1 to n are n IID observations from a continuous but unknown distribution function fx. Then we can use the sample order statistics to provide a confidence interval for the pth order quantile xi p. Note that xi p is a population quantile and hence it is reasonable to use order statistics, that is sample quantiles, to find the corresponding confidence interval. Specifically, we suggest to use the interval, that is random interval x ordered r up to x ordered s with r less than s as a confidence interval for xi p. Next, we shall obtain the coverage probability of such an interval. Note that the random interval contains xi p has a probability which is the difference of two probabilities. Number one, probability at least r observations are at most xi p, and the second one is probability at least s observations are at most xi p. Now, after a little manipulation using the properties of order statistics, we find that the above probability is equal to summation I from r up to s minus 1 n choose I p to the power I multiplied by 1 minus p to the power n minus I, which is denoted by gamma nrs. Naturally, this coverage probability gamma nrs is independent of NEF and hence the random interval x ordered r up to x ordered s is a distribution-free confidence interval for xi p with confidence coefficient gamma nrs. In practice, the confidence coefficient is set at least 1 minus alpha with specified alpha, and hence we choose s and r in such a way that the coverage probability gamma nrs exceeds 1 minus alpha is satisfied. We have discussed different hypothesis testing problems in non-parametric inference, but we did not provide any specific testing problem. In our forthcoming modules, we shall discuss one by one and also show how the cutoffs of different non-parametric tests can be used to obtain a distribution-free confidence interval for the concerned parameter.